Part 4, the solution of the transmission shift problem is extended to answer the questions not resolved in Part 3. Do the optimum shift points occur at the same engine speed for power and torque, and how are these speeds determined numerically? To obtain answers to these remaining questions, quantitative data is required for all system parameters dealt with in Part 3. These include speed versus torque data at full throttle for the engine, the gear ratios of the transmission and differential, the size of the wheel, and either a drag coefficient or some type of required rear wheel load data for the vehicle. Output torque versus engine speed at full throttle is available in tabular form from 500 to 5500 RPM in 500 RPM increments from the current specifications for the proposed vehicle design. Wheel torque required as a function of wheel speed is also available from road tests run on a similar size existing vehicle. This will be used in this analysis to determine maximum vehicle speed. The selected 3-speed automatic transmission has gear ratios of 2.5, 1.5, and 1.0. The differential has a fixed ratio of 3.95, and the proposed tire size will result in a wheel diameter of about 24 inches. An operationally defined problem based on the system behavior developed in Part 3 and the given design specifications is now required to answer the unresolved questions. This might be stated as, based on the qualitative behavior of available power and torque as vehicle speed increases, and using the given output torque versus engine speed performance, together with the specified gear train information, determine the numerical value of the vehicle speed in miles per hour, where the torque and power curves cross each other in all 3 transmission gear ratios. At this point, step 2 in the generic solution process has been completed. 2 solution concepts come to mind for solving the stated problem. One is graphical and the other analytic. The first calculates the available torque at the wheels as a function of vehicle speed in miles per hour for all 3 gear combinations for each value in the engine output chart. These torque values in each gear are then plotted on a graph of torque versus vehicle speed. The crossover points identify the vehicle shift speed for optimum acceleration. The process is repeated for power available at the rear wheels. The second solution concept requires developing an analytic equation for the engine output torque as a function of engine speed. This equation is used to determine analytic expressions for torque delivered to the rear wheels in terms of vehicle speed. Setting torques equal in the first and second gear torque equations permits solving for the vehicle speed where crossover takes place. This is repeated with the second to third gear torque equations to establish the vehicle speed for this crossover point. The process is again repeated for power. Solution concept 1 is selected as it mirrors the qualitative analysis of Part 3. The first step is to identify and list symbolically all the variables associated with the problem model of engine, transmission, differential, and wheels. Parameter units are specified to ensure dimensional correctness for numerical calculations. This effectively completes step 3 of the solution process. To convert engine speed in RPM to vehicle speed in miles per hour, the vehicle velocity is first calculated in terms of wheel speed. This is simply the wheel speed multiplied by the wheel radius, with appropriate unit conversion factors included. Recognizing that wheel speed is the engine speed divided by gear ratios results in the final equation for vehicle speed in terms of engine speed. An example calculation is presented for one specific engine speed and transmission ratio. This is then repeated for every engine speed listed and all three transmission ratios. At an engine speed of 1,000 RPM in first gear, a vehicle velocity of 7 miles per hour seems quite reasonable. A transmission with a positive gear ratio reduces speed from input to output while increasing the transmitted torque. The torque available at the wheels is calculated by multiplying the engine torque by the three gear ratios. Example calculations are presented for an engine output torque of 182 pound-feet at 1,000 RPM. As anticipated, the torque available at the wheels at a given engine speed decreases with shifting from first to third gear. These calculations represent a combination of steps 4 and 5 in the solution process. The first two columns in the chart are the given engine data in speed and full throttle output torque. The next three columns are the vehicle speeds corresponding to engine speeds for all three transmission ratios. The last three columns are the available torque at the vehicle speeds in the previous three columns, again for all three transmission ratios. At 1,000 RPM, the engine delivers 182 foot-pounds of torque. This engine output speed corresponds to a vehicle speed of 7, 12, and 18 miles per hour of vehicle speed. At these speeds, the available torque at the rear wheels is 1,797, 1,078, and 719 foot-pounds. The calculated available torque in all three gears is now plotted on a graph of torque in pound-feet versus vehicle speed in miles per hour. It is observed that the first and second gear curves cross at about 37 miles per hour, and the second and third gear curves cross at about 55 miles per hour. Shifting at these speeds will provide maximum acceleration. Referring back to the previous chart, a 37 mile per hour vehicle speed corresponds to shifting from first to second gear and an engine speed of about 5,100 RPM. The shifts from second to third at 55 miles per hour occurs at an engine speed of about 4,600 RPM. Note that the torque values are about the same in sequential gears at 36 and 54 miles per hour on the chart. This completes the evaluation step of the solution process of the torque available portion of the stated problem. The solution process now returns to step 4 to determine the maximum velocity of the vehicle. This is now easily obtained by plotting the torque required at the rear wheels as a function of vehicle speed on the previous torque graph. Using the road test load data, this chart lists the torque required in pound-feet as a function of the vehicle speed in miles per hour using the previous developed equation. For example, at a vehicle speed of 50 miles per hour, the required wheel torque is 325 pound-feet to overcome the assumed road resistance load. When plotted on the available torque curve, it is observed that the maximum velocity of the vehicle will be about 72 miles per hour, corresponding to a consumption of about 100 horsepower. The analysis just completed now needs to be repeated from the perspective of power available from the engine and power required from the road test data to determine if the numerical values of the shift points and maximum vehicle speed are the same. Power from a rotary source is the product of the output torque and speed in terms of the defined system variables and the introduction of appropriate unit conversion factors. An equation for engine power in horsepower can be developed. At 2,000 RPM and an output torque of 185 pound-feet, the engine generates 70 horsepower. Using the previous equation for vehicle speed in terms of engine speed, this power output in first, second, and third gears occurs at vehicle speeds of 14, 24, and 36 miles per hour. This chart lists the given performance data together with output power at corresponding vehicle speeds in all three gears. The previous calculated results at 2,000 RPM engine speed are highlighted. The available engine power in all three gears is plotted on a graph of horsepower versus vehicle speed in miles per hour. The crossover points on the three power curves occur at the same vehicle speed values as predicted by available torque, that is 37 and 55 miles per hour respectively. This establishes that shifting for optimum acceleration is the same irrespective of whether a torque or power approach is used. The validity that both approaches provides the same results can be further verified by determining the maximum vehicle speed using power. An equation for horsepower required at the rear wheels in terms of wheel torque and speed to overcome road load resistance can be developed in terms of listed parameter values using unit conversion factors as shown. An example calculation at 600 RPM and 270 pound-feet results in 31 horsepower at a vehicle speed of 43 miles per hour. This chart lists the horsepower required at specific vehicle speeds in miles per hour corresponding to the assumed road resistance load data. The calculated results of the previous example are highlighted. The calculated rear wheel load horsepower values are plotted on the previous power versus vehicle speed graph. The crossover of the load curve with the third gear power available curve occurs at a vehicle speed of 72 miles per hour, the same as previously obtained from the torque analysis. Hence, both approaches predict the same result. All the calculated results appear reasonable in light of the specifications for the proposed design. This brings the solution process to its final step of communicating this information in a report that addresses the original need. An example report might include the following 4 items. For optimum acceleration, the transmission should be shifted at an engine speed when torque or power in sequential gear ratios is equal. The transmission shifting speeds are the same for either a torque or power perspective. The optimum engine shift points for the proposed design are about 5,100 RPM first to second and 4,600 RPM second to third. The maximum vehicle velocity will be about 72 miles per hour. Solving the transmission shift problem provides some important takeaways that a simple description of the application of the process doesn't cover. The initial statement of need can often be vague and consequently lead to questionable initial responses. The importance of first understanding the physical behavior of the system can't be overestimated. The resulting problem statement needs to recognize what quantitative results will effectively meet the initial need. Process activity can overlap and be repeated in solution steps like model development, applying engineering principles, numerical calculations, and/or checking. Finally, the solution process procedure is of greatest value when applied flexibly, not dogmatically, using the skills of synthesis and analysis effectively. This completes the last part of the Solving Engineering Problems presentations.